Now we're working 1437 from the book. This is also very similar to some of the problems you might see on October 3rd's online homework assignment. It says, considering this reaction, the reaction of nitrogen with hydrogen to make ammonia, complete the following table. Now we're told in problem 37 that the concentrations are molarities, and I've labeled that. Okay, so that's important. We're going to be computing Kc here, but we're also told in the problem that these concentrations reflect equilibrium concentrations. And whenever we hear that, we're happy because we know something about the equilibrium state. And that's important for computing Kc or use of the Kc. Okay, so let's look how we can complete this table. Now, there's 3 different temperatures specified, and each temperature is going to have its own K value. And this is pretty typical because remember, if you change the temperature, the K value also changes. Equilibrium constants are temperature dependent. So the first one, we're given equilibrium concentrations of 3 substances and asked to find Kc. And this one's pretty easy. Because all we need to do, write the Kc expression and plug and chug. Now in this particular case, we have products over reactants, which corresponds to the molarity of NH3 at equilibrium. We've got to square that one by virtue of the 2. We divide by the molarity of the nitrogen raised to the first power times the molarity of hydrogen at equilibrium cubed by virtue of the 3. So these are the numbers that we need to plug in to plug and chug here, okay? Now, fortunately, in the problem, we're given equilibrium concentrations of all these. So it's straightforward to plug in 0.439 here, square that. Again, these have to be my equilibrium concentrations. That's the key word. I can plug in my 0.115 moles per liter here. And I can plug in my hydrogen concentration, 0.105. Raise that to the 3rd power by virtue of that 3. So that's the mathematics that we need to do. If we work that out, the number that I got was 1447 for my K. That's my Kc. Easy as that. All right, that one's pretty easy. Now, the other problems, B and C, are a little bit different because they ask us to find different information. This was the forward problem where we could solve for Kc directly, but in the other examples, we're actually going to be asked to find some concentrations. So for instance, here in part B, we're asked to find the hydrogen concentration. That's unknown. But in problem B, we're told that the K at that temperature was equal to 9.6. So we raise the temperature a bit, the K drops, okay? But it's equal to 9.6. That describes the equilibrium position at that temperature. So we're going to honor that and write our ratio. Products divided by reactants raised to stoichiometric coefficients. So my ammonia goes up here again, just as it did before. I'm going to square that. In the denominator, I'm going to write my nitrogen concentration and my hydrogen concentration. Got to raise this one to the 3rd power. All right. So you see the form of our generic equilibrium constant expression. Now all we need to do is plug in the things that we know and solve for what we don't know. I was told in this problem, part B, the concentration at equilibrium of N2 was 0.11. So I can plug that in there. That's my molarity at equilibrium. What else do I know about this, okay? Well, in trial B, at equilibrium, my concentration of NH3, ammonia, everybody's favorite cleaning material, right? That's an aqueous solution of ammonia. Ammonia by itself is a gas, but here, 0.128. That would be my molarity of that. Now, as I look at this carefully, I say, okay, I got to square this. Well, where's my unknown? Well, it's my hydrogen concentration. And sure enough, that's what I need to solve for, okay? So all I need to do is rearrange this after plugging in. solving for the hydrogen concentration. So the first thing I would probably do, as I was looking at this, is I would try to isolate this variable first, okay? And I'd likely do that by doing something like 9.6 multiplied times 0.11. So I multiply both sides by 0.11, so it clears this fraction. I multiply it by this as well to get that. Okay, so I bring that out basically. And then I would also work to divide by this number, okay? Did that, it would be 128 squared. Divide both sides by that, and of course that would equal whatever I'm left with, which right now appears to be 1 over concentration of H2 raised to the third power. Okay, so by doing that, I could generate, this kind of equation basically, where I could solve the left-hand side, and that would be 1 over the H2 raised to the third power. Now, let's see, where do I want to work in? How much room do I have over there? Oh, I got plenty of room. Okay. Now, if I'm going to work towards solving that, move my cleaner, I basically invert both of these such that my H2 raised to the third power is equal to 0.128 squared over 9.6 times 0.11. Alright, so I just basically take the inverse of both sides to get closer to solving for the H2 concentration. Now, the solution is apparent at this point because all I need to do is take the cube root of both sides. And I can solve directly for my H2 concentration. And that's what I'm going to do. And when I solve for that, my H2 concentration ends up being 0.2494 moles per liter. A little under a quarter of 1 molar concentration. Okay, so that shows an example where we're solving for the concentration of one of our materials, based upon a value for an equilibrium constant and concentration of other materials at the equilibrium position. Okay, this third example is more or less exactly the same as that, so I'm not going to work through that. It's just a different temperature. You have to use a different K, and you're solving for a different substance, but the process is essentially the same. You just use different numbers for concentration and the K value. So that's an example of this type of problem.